Welcome back, everybody. So we have the pleasure now to hear Andrew Lawrie. We'll talk about bubbling for the harmonic mass flow. Thank you.
Thank you, Sue. And thanks to the organizers for the invitation. So very happy to be here. Okay, so my talk is also not about mathematical GR or about dispersive PDEs. So
That's true. It's only a few seconds.
okay.
It's AI. The moment you said it's not about it.
Yeah. Okay. All right, I think it stopped except for the flashing. But hopefully there'll be I'll try to emphasize some of the technique that we use in this problem that maybe has some parallels or some. So it's about harmonic map heap flow, and it's joint work with Jan and Wilhelm Schlage. And so the objects we'll consider are mappings from R2 into the two spheres sitting inside R3. And to such a map, you can associate the Dirichlet energy. This is the gradient of U. So use a vector in R3, and this is its gradient, dx. And okay, so this is a natural object, and it's classical studied. And so what we'll be interested in are the critical points of the energy functional. So I can make a definition. I wrote U, but I'm going to call them omega. So omega is a harmonic map. If and only if it's a formal, so I'll be a bit vague for a second. So it's a formal stationary point for the energy functional, and you can find the Euler-Lagrange equations, and you see that the requirement is omega be perpendicular to the tangent space of S2 at omega. This doesn't look like a PDE, but what this says is that if you project onto the tangent space, you should get zero. Sorry, this makes sense. So plus, not omega. That's omega. That is also true what I wrote. Trivially true. But the Laplacian of omega is perpendicular to tangent space, and if you project onto the tangent space, you get the harmonic map equation. So Laplacian omega plus omega grad omega squared is equal to 0. And there's a old theorem. So these objects are completely understood. And so now I'm going to tell you what I mean by solution to this equation. So omega is so if I take an H1 function, I'll call this H dot 1. So weak solution. So to this equation, so if omega solves it weakly, then there's then omega is C infinity smooth. So this is proved by in the 90s, and it builds. I mean, there's older work. So this is Halern's theorem, and before this, there's theory of Sachs-Uhlenbeck, Eales-Wood. So there's more to say. So omega C infinity smooth. So weak solutions are smooth, and extends to a harmonic map from S2 to S2. So you can remove the singularity. This is the Sachs-Uhlenbeck theorem, but also implied by Haller's work, later work. So not only that, it's known that so this is work of Eales and Wood, that omega is conformal. There's a plus minus conformal up to orientation. So meaning it satisfies Cauchy-Riemann equations, and then you can identify such harmonic maps with the holomorphic functions from S2 to S2. So I can think of these as maps from. If I think of these maps as from C infinity to C infinity, these are the rational functions. So the only holomorphic mappings from C infinity to C infinity are the rational functions. P of Z over Q of Z. These are polynomials. So rational in Z, and then I said this is conformal up to orientation. So rational in Z or in Z bars. So rational functions in Z or Z bars. So these are completely classified. So we understand this equation completely. And what I'll talk about today is a related So what's the harmonic map heat flow? It's the L2 gradient flow, so negative gradient flow. The energy functional E. This is dTu is equal to the positive U plus squared. And I'll call this right hand side, this is typically called the tension of your fluid, done by script T. So I'm on my P flow, and it's the initial value problem. For this, give myself initial data, initial mapping from S2 to S2. And this was introduced by Eels and Sampson in the 60s. This heat flow to with the idea is you want to take an arbitrary map from S2 to S2 and then try to find a harmonic map. So the L2 gradient flow is a way to decrease the energy the quickest. And the idea is that these are the equilibrium points of the energy functional. So the harmonic map flow will hopefully find a harmonic map as T goes to infinity. And so the idea here for using, you could try to use using variational methods as well. But the heat flow is a natural candidate to do this because it does so while preserving the homotopy class of the map. So you give a continuous deformation of a map from S2 to S2, preserving the degree of the map. Of course, okay, so in this case, this is going to fail to find harmonic maps. In the case I wrote down, this, Eels and Sampson introduces this a more general setting. You can just consider maps between Riemannian manifolds. So this is the general setting considered by Eels and Sampson. And in some cases, they prove that, in particular for negatively curved targets, that the harmonic map heat flow, which is a different equation, general equation, finds a harmonic map as T goes to infinity. So we're going to also just try and study the long time asymptotics of this PDE, and it's going to fail to find harmonic maps, but what it does exhibit nice structure. So there's singularities, and they're all bubbling type. So there's an old theorem. Beautiful theory of Struwe about this equation. So Struwe, 1985. Can't draw an 8. Struwe, 1985. So he solved this equation. So for initial data in H1. So H1 initial data. Then there exists a maximal time of existence for the associated data. So maximal time. Possibly finite, possibly infinite. And a unique solution. Unique harmonic map heat flow. UT. It's regular. Smoothing, smooth function. Once you let it go for a bit. So it's regular, and so then the energy identity holds. So I'm gonna try and I have a bunch of bullet points here. So the energy of U at time t. Is the energy at time 0. And this is like coming from someone who often studies nonlinear wave equations. This is this control of this type of factor. This type of term is kind of amazing. I can't get enough of this. And I'm going to write this slightly differently. So this is so U solves the equation. So dt of U is given by the tension. So this gives me control of tension of U of t. Control the second derivative of U. L2. So we have the energy identity, which I'll use in the talk. And then this maximal time. So t plus. If you say something about maximal time, you should give some characterization of the maximal time. So I'll tell you what I mean by maximal time. So t plus is finite. It means there's energy concentration. So so characterized by then there exists a finite collection of points in R2, and an epsilon not positive, such that for every R, the limit as t tends to t plus the energy. If I just look at the energy of U, localized to a disk about these points of radius R, this is this is always always bigger than epsilon naught. So these so T plus is finite means I can find these what are called these bubbling points. I'll tell you what I mean by bubbling in a second. But for now, this means that the energy concentrates at these points. So for every r bigger than 0, if you no matter how small the disk you look around this point, there's always epsilon worth of energy there. And they're called bubbling points because what Struwe showed is that you can, so for each of these XL, there exists a Tn tending to T plus, a sequence AN and R2, and lambda n tending to 0, such that if I look at, if I rescale U and translate U along the sequence, so U at Tn, a lambda n, this converges H look to a non-trivial harmonic map, so non-constant harmonic map. So this is what's called bubble. So if I rescale along the flow, I zoom in, I see a harmonic map, at least one harmonic map. Okay, so this is the Struwe theory. And this so this is 1985, beautiful 1985 paper. Maybe I want to say one more thing about this. So the last point is that if I look away from these bubbling points, then I have a well-defined weak limit. So so there exists U star, and Struwe finds this in H1 function U star, such that U of T converges weakly to U star, and you have strong convergence away from if I excise these bubbling points, so strong local convergence away from the bubbling points. As to this. So this is in H1. Okay. And then okay, so this is Struwe bubbling. And in addition to this, we can ask for more. Let's give some qualitative description of the singularity formation. And then about 10 years later, I tried to learn this literature. It's a bit confusing, but I think the first result is 10 years later, in this paper of Qing from 1995. The fine structure of the singularity formation along a sequence. So it's the same setup. So just kind of continuing this theorem. If I look at one of the XL as before, the bubbling point. I can find an integer m bigger. So what Qing proved is that there's Struwe found one harmonic map, one harmonic bubble. And Qing proved that there may be more. So if I take a bubbling point, there's this m bigger than 1 and non-trivial harmonic maps, omega 1 to omega m, and a sort of sequence Tn tending to T plus, non-trivial harmonic maps omega 1 through omega n, such that you have a bubble tree decomposition. So I should say what else there is. There's so scales. Oh. And then j goes to 0, and then a and j number 2 tends to XL. So this a and XL first here. So you have a bubble decomposition. So if I look at U along the sequence of times, I subtract off the radiation, then this looks like a sum of bubbles. So a sum from j equals 1 to m omega j, translated and rescaled. These parameters. And I want to match up their endpoints at infinity. Yes, this is limit as x goes to infinity. Omega jx. This goes to 0. and H1 in a disk about XL radius. So for every small disk about XL. And this bubble, so this is the Qing bubbling, bubble decomposition. So you don't just see one bubble, but you see possibly many bubbles. And what this decomposition immediately applies to energy identity. So, which is seems to be an important result in geometric analysis community. So, limit as t goes to t plus. If I look at sufficiently small disk about XL, then this splits into the energy of U star in this disk plus the sum of the energies of the bubbles. And which I should have told you on the previous board. So the energy, that's important for the talk. The energy of harmonic maps, if I have a harmonic like omega, is equal to 4 pi times the degree of omega. Maps about a degree. Where degree is any notion of degree, like they all coincide. In this case, it's a smooth function. So the degree of these is a rational function, Brouwer degree, any degree you like. We're in a nice smooth setting. Okay. Okay, so this is the Qing theorem. Where does this come from? How do I I want to say quickly, so this is a deep theorem. I'm not going to even come close to doing the proof, but I want to show you the main ingredient of the proof. The main ingredient of the proof is it's an elliptic compactness lemma. So elliptic compactness or elliptic concentration compactness lemma. Which says the following. So it's a concentration compactness of Pelley-Smell sequences. So if I have a sequence of maps, with bounded energy, so I want to have some Pelley-Smell type conditions, and then so Pelley-Smell condition is like this. So something like not Pelley-Smell condition, but a Pelley-Smell sequence, something like this. But I'm going to localize it. So energy of UN is bounded by C, and there exists a rho n sequence of positive numbers such that limit as n goes to infinity rho n times L2 is equal to 0. So this is the tension of UN, and this is the formal gradient of DE. So if I have this Pelley-Smell type sequence, then UN admits a bubble decomposition. So a bubble decomposition, as in the previous board, a racing force, this U star here. Okay, so this is an elliptic compactness result. There's and this is there's a so admits a bubble decomposition, and there's been lots of refinements to this theorem. This is proved by Qing. In this setting, if I assume that the tension's identically 0, so if I just take sequence of harmonic maps, you have the same. This is proved earlier by Parker and Yost, or Yost and Parker. And for results, so sequences of harmonic maps still can bubble. And then there's been various refinements by Qing Tian, Ding Tian, Lin Wang, I'm reading the order of things. Lin Wang, and refinements meaning, so you can ask, I gave a bubble decomposition in energy space, but then one can ask more. So this is a big deal to prove that such a decomposition holds in L infinity as well. You're right. So this is L infinity is important, right? It's on 2 dimensions. So so H1 functions are not continuous, and so these in these refinements, the same theorem holds if I replace the same type of theorem holds so in H1 I'm in L infinity too. Yeah, right. And if you want to think of this as sphere valued objects, then you want to know about all infinity as well. It doesn't really make sense in the energy space. Energy space doesn't see constants, right? So, okay. So this is the main ingredient in the proof, and you can ask, okay, where do I get such a Pele-Smell sequence from the harmonic map heat flow, and just from this condition here. So I have a bound on the tension. So in particular, this is finite. So I can run this to the maximal time. It's finite. Okay, and any sequence is of course a Pele-Smell condition. So if I allow this row in here, so what matters is the scale at which you find this. And so, but this bound on the tension tells me that I have a Pele-Smell sequence up to scale to square root of t plus minus tn. So there exists a sequence. Square root of t plus. Goes to 0. So this integral is finite because the log integral diverges. You can find a sequence like this. So this gives you, so this plays the role of my rho in, and so this is the square root of t plus minus tn is the parabolic scaling. I don't want to clean it. Absolutely. Sorry. Yeah, so no square. This is the parabolic scale. So I have bubble decomposition up to the parabolic scaling, and then I have to so then I'm missing to control the energy outside of the scale, but I can I'll mention these some energy propagation estimates to do that a little bit later in the talk. Any questions up to this point?
So you needed some condition on the rho n in the.
No. Sorry, but yeah. So I haven't, I should write some more words here. Yes.
Okay.
So bubble decomposition, up to scale. Yeah. So this up to scale. Sorry. Yeah. Up to scale rho n. So, right. So this is the, this tells me up to what scale I can expect. I see bubble decomposition. So important, you rescale this by rho n, and rescale the map, and then I get the tension, so after rescaling by rho n, then this is like equivalent to saying the tension goes to 0. So then it gives you bubbling at scale 1. But yeah, undoing the scaling, I get bubbling up to scale rho n. And this is what I mean. So this gives you, this is my rho in here, and I get bubbling up to scale square root of t plus minus t. Okay, so all right, so some questions. So this is the late 90s, is when these results were proved, and then it asks, there's some questions that come up after this theorem. And one question, a deep question that seems largely unanswered is the regularity of U star. So U star is given by taking this weak limit in H1, and you can ask, is this a continuous function? I think this is a completely open question. U star more regular than just being an H1 function. But then the question, so this question I'll discuss for the rest of the talk is what this is a sequence of times along which you have this bubble decomposition. And then you can ask, so there's about the uniqueness of the bubbles. So if I have a different sequence of times along which I have another bubble decomposition, do I see the same harmonic maps in the decomposition? This is called the uniqueness question. And then the related question is, do I see bubbling in continuous time? So can I prove that this happens rather than along a sequence of times, so it happens in continuous time? And I'll discuss this. This is what the topic of the talk will be. Where should I read? Let me mention that there's been some progress on these questions up to about 20 years ago, it seems. So about the uniqueness question, Topping proved that the meaning is the bubble decomposition unique, proved that the answer in general is no. But he gave some construction where uniqueness fails with but he gave himself allowed himself a pathological target manifold. So not in the S2 setting is expected to someone it's an analytic target expected to have uniqueness, I guess. And in that setting, Topping made some progress in the late 90s thesis, beautiful thesis in the late 90s and early 2000s, where he showed that I've been mentioning the finite time case, but in the global case, you can ask the same type of question or even the same type of bubble decomposition for a global flow. And topping in the global setting proves that the points of energy concentration are unique. So in the finite time setting, these are clearly it's clearly a unique set of bubbling points by the Struwe theory. But in the global time setting, you can wonder if the points where energy concentrates move around. And Topping proved that they don't, as long as you assume that all the bubbles in the decomposition have the same orientation. And he also proved uniqueness of the weak limit under this setting as well. So the bubbles are all holomorphic bubbles. They are all anti-holomorphic bubbles. Then you have uniqueness of the bubbling points in the time case and uniqueness of the weak limit. And this is quite a strong assumption, as I'll discuss in a little bit review it. Is it you can we'll try to understand how bubbles interact with each other. Well, we're trying now to understand how bubbles interact with each other, and if bubbles have the same orientations, then they don't interact at all. So it's only bubble anti-bubble that interact. They can be attracted. There you can have attractive interactions or repulsive interactions. The bubbles are the same orientations, so have no interaction. So to that setting, there's been some progress. Okay, so I want to discuss continuous and time bubbling, but first I have to say some more about harmonic maps. So there's scale and center. So I want to give a notion of scale for harmonic map and what this harmonic map omega. The scale of harmonic map for me will be I find a disk that contains almost all the energy of the harmonic map. So if I give the harmonic map omega its scale lambda omega, I'll define to be the nth overall lambda positive, such that there exists an A and R2 with the energy of omega on the disk sensitive raised lambda is bigger than or equal to the total energy of omega minus gamma naught, where gamma naught is a fixed, so its notional scale depends on this number gamma naught, but I'll take gamma naught, it's going to just be a fixed small number. So this is the scale of a harmonic map. It's just the radius of a disk that contains most of the energy, and the center of omega, A omega, is NEA. So this notion of scale is uniquely defined. So this is uniquely. A is not uniquely defined, but defined up to radius lambda. The center of a harmonic map omega is NEA such that the energy of omega in the disk centered at A of radius lambda omega, which is defined above, is bigger than or equal to. So this is my notion of scale and center of harmonic map. And I wanted just give a quick example to say that this is capturing something, but not everything about a harmonic map. So I want to think of a harmonic map, and I'm going to try and draw you its energy density. And you can imagine it energy being concentrated in two small disks. And the scale of this, so I need a disk that captures all of the, almost, and the energy is quantized, right? So the energy of each bubble is at least 4 pi, 4 pi. So each of these disks has 4 pi worth of energy in it. I can't take a smaller disk to capture the scale. So the scale of this harmonic map is like this, and the center should be right here. So this notion of scale misses sort of the interior bubbling life of harmonic maps. And this is important going forward. And in particular, right, I can find a sequence omega n of harmonic maps with scale 1. So I can imagine this to be scale 1 and center 0. But omega n tends weakly to a constant. So this notion of scale doesn't see it doesn't magnify things. Okay, but I need something to work with. So this is scale and center, and then I want to define a notion of a bubble configuration. So a multi-bubble configuration, we'll call those MBCs. Capital omega be a finite sequence of harmonic maps. And the first element is a constant map. and then the -1 through omega are non-constant harmonic maps. And then a multi-bubble, 2 omega x is a sum like this, where it's omega not constant plus the sum from j equals 1 to m of omega j x minus the endpoint at infinity. So these are multi-bubble configurations, a sum of harmonic maps. And then for a given map to the sphere, maybe I should just keep writing on this board. For a given map to the sphere, I can define distance to a particular multi-bubble configuration. So fixed multi-bubble configuration as follows. So I take the distance between a map U and a multi-bubble configuration Q of omega, localized to a disk in R2 of radius rho, is I just take the energy, I just take the difference of the energies on this disk. And then I want to penalize, I want this to be a multi-bubble configuration. I don't want this, I want these harmonic maps to either live at different scales or at different points in space, just like as in the bubbling theorem. So I should add a factor plus over j not equal to k lambda of omega j lambda k plus lambda omega k. Sorry, I didn't write this in the omega j. Lambda omega j. I want at least one of these ratios to diverge. If for the distance to be small. And then I want my last factor is I want this to be happening. I want the bubble decomposition to live strictly inside this disk. So I want there to be some distance between the bubbles and the bubbles in the disk and the boundary of the disk. So plus sum from j equals 1 to m lambda omega j, and I divide by the distance between the center, the relative distance of the center and the boundary of the disk. Like this. So my distance between you and a multi-bubble configuration is small if I'm close in energy, if the bubbles are well separated in scale or position in space, and my bubble decomposition lives strictly inside this disk. So in our paper, our definition is more complicated than this. So we include more, including like L infinity closeness as well. So each bubble comes with a scale and center. So I take a harmonic map and I'm defining its scale like this on the board above. This is this sort of weak notion of scale. So it's not a and then later if you want to take a fixed harmonic map and you can rescale it, etc. Then so this is a good point. So which I should say here. So if I take a harmonic map omega and I rescale it minus b divided by mu like this, translate and rescale it, then and I call this twiddle, say, then the scale of omega twiddle is roughly mu, and the center of omega twiddle a of omega twiddle. So if I take a fixed harmonic map, which its scale is roughly 1, its center is roughly 0, and if I rescale and translate it, I want these notions to coincide. Okay, so this is my distance to multi-bubble configurations. And like I said, in practice, we also include L infinity, but I just want to stick to energy for the purpose of the talk. And then let me state the theorem. So not quite. So this is distance to a particular multi-bubble configuration. And then And next I'm going to define my proximity function to the family of multi-bubble configurations. So I'm going to take inf over all possible. So I'll define delta of u to a disk of radius rho centered at y, is I just take inf over all multi-bubble configurations to omega of d u q omega. So this is distance. This is my proximity to the whole family of multi-bubble configurations. This is a distance to a particular one, and then I take an arbitrary Mach view and I try to find the closest multi-bubble configuration like this. And the theorem with the end that I schlag is if I take a harmonic map heat flow. So I take a harmonic map heat, take the Struwe flow. And it's either a global flow or it develops singularity in finite time. I'll take the result in finite time. The same result holds for global flow. So if t plus is less than infinity, then the distance, so the limit as t goes to t plus of u of t, so t plus. And then for every y in R2, the distance between u and multi-bubble configurations about y at scale t plus minus t, so the parabolic scale goes to 0. And so I mentioned before that this notion of scale doesn't pick out interior life of the bubble. So I don't want to know just this, that I approach multi-bubbles at scale t plus minus t. I also want to say that I approach multi-bubble configurations if I looked at any smaller scale as well. And then for every x of t tending to y, and then rho of t much smaller than square root of t plus minus t. If I look at any smaller disk, I'm going to say it here, then the distance delta goes to 0 on these smaller disks as well. With a caveat, so provided I didn't just by accident, choose a disk that is exactly at the scale of one of the bubbles. So provided there's a neck, so there's r of t tending to infinity, little r of t tending to 0, such that the energy of u of t on this neck. So if I look at this annulus, so here's the disk of radius rho, here's the disk of radius rho, and if I look at an annulus like this, so disk x of t, r of t, rho of t, minus the disk of x of t, or r of t, goes to 0. So as long as I have energy evacuating from this neck, which means I didn't pick exactly the scale of, so this would fail if I looked at exactly the scale of one of the bubbles in a decomposition. So as long as I'm not looking at exactly the scale of the bubble, you can find such a neck, and then delta goes to 0 on these smaller disks as well. And the same result in infinite time. Okay, so this doesn't solve the bubble uniqueness problem. Because it tells me I approach the family of multi-bubble configurations, but I'm not giving any dynamics along this family. But what it tells, it's telling me something.
Sorry, can I ask a question?
Yeah,
that please there. So how does the distance from u to q depend on u in the second term?
No, so this term penalizes, it doesn't. So this term penalizes so I want you asking, when is distance small, right? So this distance is only small if I look at multi-bubble. Only want to look at multi-bubble configurations that are truly look like multi-bubbles. It doesn't look like just a glob of stuff. So if this is a nonlinear problem, right? So I can't, if I just add two harmonic maps, I don't look like at the same scale. I don't look like a harmonic map anymore. So I want the harmonic maps in the decomposition to be either vastly separated in scale, so living at vastly different scales, or vastly different.
This separate. So
Yeah, so I want the bubbles to be well separated somehow, either in scale or relatively in space. And so this doesn't, this is penalizes having a glob, a big blob of stuff that's doesn't actually look like sum of bubbles. And same for this last term, it just tells me I want to have a neck around my disk where there's no energy. So let me tried to tell you. Sorry, let me make one other quick comment. So I don't solve the uniqueness problem because I haven't told you what the dynamics are on this family of multi-bubble configurations. But what this does tell me is that so we had the sequential result of Qing, the sequential bubbling result. So there exists a sequence, and the sequence is a special sequence. It's given by Paley-Smale. There's some type of it's a Paley-Smale sequence that you get from the energy dissipation. And what this tells me is that in fact, I have bubbling, sequential bubbling, as in the Qing theorem, but along any sequence of times. So I take any arbitrary sequence of times, and after passing to a subsequence, okay, I see a bubble decomposition, as in the Qing theorem. So this sort of removes. So this tells you something about harmonic map flow. This is not true in general for sequences of maps. It's specific to a flow. Okay, so some elements of the proof. So how to prove it. So the idea, and this is why I hope this is a bit relevant for the audience. The idea for the proof, the rough idea, intuition comes from dynamical systems. So I want to say that I'm going to argue by contradiction. And if I think of my manifold of multi-bubble configurations as this point here, the failure of this theorem would be, I know the Qing theorem. There's one sequence of times where I approach multi-bubble configurations, and if the theorem fails, there'd have to be some disk around, some ball around the family of multi-bubble configurations where I get close to and then move far away from multi-bubble configurations infinitely many times, right? And so this to me sounds like theory of omega limit sets and dynamical systems. And what we're going to try and prove is a no return property. So this type of coming close to moving away from this multi-bubble configurations infinitely many times can't happen. And so in dynamical systems, you try to find like Lyapunov function or something like this, and we're going to interpret all these things very loosely. But again, the key ingredient is going to be this energy dissipation. This is going to give me a kind of a Lyapunov functional to work with. Okay, so this is the intuition, but to make it happen, this seems to be the key ingredient. So I'm going to find what's called minimal collision energy. So I'm going to study I'm going to try and study. So how do I move far away from multi-bubble configurations? You can imagine if bubbles come toward each other. So if I'm close to multi-bubble configuration, I have bubbles well separated in space or in scale. To move away from it, you can imagine the bubbles coming close together and interacting, colliding, in some way. So I'm going to try and rule out collisions for this problem. And to do this, I'm going to define what's called the minimal collision energy, which is defined as follows. So it's the smallest, and here I'm going to rely on this quantity. So it's an induction type argument also. So I'm going to rely on this quantization of the energy. The smallest integer k bigger than 1, such that there exist sequences. So sigma n tending to t plus, tau n tending to t plus. So these are going to give me time intervals. So sigma n plus tau n. Points in space. So yn and R2. Rho n's are my radius of disks. The sequence epsilon n goes to 0 and eta bigger than 0. Eta is going to be my distance to multiple configurations, such that, so this is so the definition is the smallest k, such that there exists such sequences with the following properties. My distance at time sigma n to multi-bubble configurations is small, epsilon n. 2, my distance, so this is my bubbling time, so I'm close to multi-bubbles here. My distance at time tau n is big, it's fixed bigger than eta for every n. 3, the length of these intervals, I'm going to call these collision intervals. So sigma n tau n is my collision interval, and the length of this interval is much less than this parabolic scale. Rho n is the scale of the disk of all that's happening. And 4, so this minimality is that that the energy at my bubbling time on this disk. So there, I should show you where k comes in, converges to 4 pi k. Sigma n's are the time where I see bubbling, so I have this quantization of energy happening there, and k, the minimal collision energy, is defined like this. So this this notion is well defined in the event that the theorem fails. So I won't show you the proof of that. Right, what else? But so I won't show you why this is well defined. But I want to show you what the key point of this definition is. Is that it's going to give me, so I mentioned I want to prove a no return lemma. So I want to leave the neighborhood of a multi-bubble configuration infinitely many times. But this is, you kind of, if you want to do something with this, you want to know how long I stay, you know, you want to have some cost of leaving. You want to associate the leaving with some type of cost. And here, so I want to try and estimate, relate how long I stay away from a multi-bubble configuration. So how long are these collision intervals? I'm going to try this notion of minimal K is going to give me the ability to relate the length of these intervals with the scale, the largest scale of the bubbles involved in the collision. So there might be many bubbles at many scales, and I can't control all of the collisions, but I want to relate this length of time to the largest scales involved in collisions. And this is the key lemma. This is the key lemma. Is that in this same setup, so eta is fixed. So let's, this is K exists, and then I give myself some parameters. So existence of K, well, K being well defined means I can find some collection of parameters like this. Let's take some choice. Then there exists an epsilon bigger than 0, and time Sn, or such that for every such that if Sn inside sigma n tau n, I'll call these intervals in, satisfies my distance to multi-bubble configuration at time Sn is less than or equal to epsilon. So I want to think of epsilon as being is much smaller than eta. So eta is fixed, and so for every eta sufficiently small, there exists an epsilon, such that if I'm epsilon close to a multi-bubble configuration, then the length of this interval tau n, the right endpoint of this collision interval minus Sn, is bigger than or equal to epsilon times lambda max n squared. So let me tell you what lambda max n is. It's the scale, like I said, it's the scale of the biggest bubble involved in the collision. So so where lambda max is where this is so where so lambda max n is the maximum of the scales of bubbles omega j, where omega j are any harmonic maps such that the within U is within epsilon, or the distance epsilon from the multi-bubble with these harmonic maps. Omega. So I take any multi-bubble configuration that almost realizes this inf, and I look at the scale of the biggest bubble. And here, this is, or this, at least this is only a finite collection of bubbles, so this is a well-defined notion. There may be many bubbles roughly of the same size, but bigger than one. And then this interval is at least lambda max long. And once you have this, it's game over. Because so once I prove this lemma, it's game over because so it's right over here. I have my boundary. Maybe I shouldn't write over there. Right over here. It's game over because or let me tell you why this is true first, and then I'll tell you why it's game over. But okay, game is over. Okay. Yes, I want to show you why this is true. More than I want to show you why the game is over. So it's over because of the energy dissipation. But let me try and tell you why this lemma is true. So it's basically if it was in a wave equation setting, you'd think, okay, it's this finite speed of this should be a consequence. If I just forgot that I was dealing with a parabolic equation, this is trivially true by finite speed of propagation. So somehow, almost, not really. But what I mean is, if the interval was much shorter than lambda than the scale of the biggest bubble, then it should take. It should take, if a bubble is at scale, if I have a wave equation at a bubble at scale lambda, it would take time lambda for this bubble to move. So if the time interval is very short compared to the scale of the biggest bubble, that bubble can't be involved in the collision because it doesn't move. And in a parabolic equation, you don't have finite speed of propagation, but you really kind of do, right? You have so parabolic, what does you have? I could think of how long it takes for a mass to move for a parabolic equation to move some mass. So if I have 2 times T2 T1, the energy at time T2 on a disk, say about x of radius r of 2r, so if r is less than or equal to the energy at time T1, 2r plus some factor plus a constant times r squared. So if I had small energy at initial time a disk of radius 2r, and I only evolve for a time T2 minus T1 much less than r squared, then energy it controls my energy in a disk of radius r at the later time. So this is kind of a parabolic analog of finite propagation speed. And okay, so how do I use this? Well, so suppose the proof of the lemma. So suppose the lemma is false. Then I could find times sigma and twiddle, such that tau n minus sigma and twiddle is much less than lambda max n squared. So I can find some times like this inside my collision interval, where at sigma and twiddle, my distance is going to 0, and my distance at time tau n is eta away. So here I want to imagine one of the lambda max bubbles. So this is a disk where the bubble at scale lambda max is concentrated. At time sigma n, I have multi-bubble configurations. But then by parabolic localized parabolic regularity theory, if I look at the same disk at some time that's much shorter than lambda max squared, a multi-bubble configuration at scale lambda max n can't get destroyed. It stays coherent. But then I know this later time I'm far from multi-bubble configurations. So there must be collisions at a smaller scale. So I should be able to find smaller disks inside here, where at this time I have multi-bubble configurations like this. So this is supposed to be a 2-bubble. But then at the later time, I'm going to take this disk sufficiently large, so I have some space in between here. I can take this disk sufficiently large so everything is sort of trapped inside this disk. But then inside the disk, I have a collision. So my looks like a heart, but I don't know. Me and Jacek and Wilhelm discussed very long time how to draw a multi-bubble collision, and this is the best we've come up with. This is supposed to be 2 bubbles concentrate at the same, 2 bubbles same size concentrating at the different point in space, and then here they're supposed to merge in space and no longer looks like a multi-bubble. So this should happen at a smaller scale. But then I have some energy. I have at least some energy at lambda max. Like some lambda max is one of the scales of the bubbles. So inside these smaller disks, I should have energy less than 4k minus 1 pi. And the same here, because I can make this disk a little bit bigger than this radius, so less than 4k less than or equal to 4k minus 1 pi. And now this I have to work, but I can contradict the minimality of k like this. So this is a notion. So this tells me that collision intervals are sufficiently long. And now the last, sorry, I'm running out of time. I promised the game would be over. And I can hopefully do this in 1 minute. Now the game is over. So So I have my multi-bubble config. So this is a different picture. This is a dynamical picture now. My multi-bubble configurations are this dot. This is a whole manifold of these guys. And then my disk of radius eta, where I'm far from multi-bubble configurations, and a small disk now of radius epsilon. So by the lemma, I give myself this number epsilon. It's a fixed number epsilon. So find Sn as in lemma, Sn and epsilon, where now I can take my distance is bigger than or equal to epsilon for every t in Sn tau n. Right, so I just need to get I can take my distance, define this Sn to be the largest time for which I'm distance epsilon away from multiple configuration, and I'm always bigger than epsilon after this. So I'm always outside here. And then importantly, so that tau n minus Sn is bigger than or equal to epsilon times this lambda max scale, lambda max squared. But now, so I have this. On the other hand, what this tells me is that I have to have my tension has to be big on this whole time. It's bigger than or equal to C naught. Why? Otherwise, I have elliptic bubbling at so I have bubbling at scale lambda max n, and then it's not straightforward. Not a straightforward argument at all, but this gives me bubbling. So if this were to fail, I'd have some sequence of times where I had this quantity going to zero. Elliptic bubbling tells me I have bubbling at every point at scale lambda max n, and then I have to show that this gives me bubbling at scale rho n, at the bigger scale. Lambda max n is a much smaller scale than rho n, so I have to get bubbling on the whole disk as well. And there we have to fight with energy propagation estimates, L infinity propagation estimates. In fact, we use Tao's. I learned Sungjin. I learned Tao's Strickhart's estimates for the Strickhart's type estimate for the heat equation to propagate small L infinity. We use this as well. But okay, this would tell me so I obtain something like this, because otherwise I'd have bubbling. I can't have bubbling because I'm distance epsilon away from multi-bubble configurations. But now I have infinity is just given by the sums of one C naught, I guess, epsilon, which is less than or equal to integral from n. T, which is less than or equal to the sum in n. I may have messed up the constants here of SNT at tau n of tension and this is bounded by, since these are disjoint intervals, so this is bounded by the whole integral 0t plus of the tension. And this is less than infinity by the Struwe theory. The contradiction. So this is, I mean, this is this wonderful bound. Like kind of immediately, we started thinking about this problem used to, we come from nonlinear wave equations, and this is like a gift from the. I love. I'm going to become a differential geometer. I'll stop there.